Okay, Carsten, we are going to start. So welcome everyone. It is our great pleasure today to welcome Professor Carsten Rockstuhl from the Institute of Nanotechnology and the Institute of Theoretical Solid-State Physics in Karlsruhe, Germany. So today, Professor Rockstuhl will talk about the T-matrix approach to describe them all, materials, metamaterials, and metasurfaces, and this is perhaps some reference to Tolkien, but Professor Rockstuhl, please.
Yeah, okay, so thanks, Sebastian, for the introductory word, and also thanks, Bogdan Muammer, so inviting me to this very nice seminar series also, and to present to you today some of the recent work basically that we have been doing. So I've been using this opportunity here to summarize a little bit the larger number of basics that we put in place in the past years in order to describe from theoretical and numerical grounds mostly metamaterials and metasurfaces, yeah, or let's say photonic materials in general. But as you will see, we also have this aspect now included that we can consider also molecular materials and describe complex materials made out of individual molecules, or at least when it comes to optical description quite precisely. And that's why the title was chosen, so a T-matrix approach to describe them all. Yeah, and this is to a extent, this is also a technical talk. So to make you also familiarize yourself with this sort of T-matrix technique in the case you have not heard it so far. But of course, I'm also going to sprinkle in overview of a larger number of applications that we have been working on in the past years. So to illustrate the applicability and the scenarios where that technique is really useful for theoretical and numerical explorations. And before I start, I would like to thank, of course, those people that did the work and on which I'm heavily relying on. So for those that know my group a little bit, just for my background, so we have 4 different subgroups at the moment. So one of them is working with quantum optics, mostly in integrated systems. One of them is working mostly on tools from the field of machine learning or design tools really for photonic materials with properties on demand. And the 2 subgroups that contributed most heavily to this particular talk here are a smaller quantum chemistry subgroup, so led here by Marian Kristic and Christoph Holzer, and of course the scattering subgroup that Ivan Fernandez-Corbatong is mostly responsible for, and they did a large amount of work really together with other postdocs and also PhD students. Yeah, and I thank them very much for the work that they also do here. So when I say to start that I would like to develop a kind of comprehensive framework, yeah, so to discuss optical properties of materials, I really have to make actually only a single assumption, so that concerns the way we are going to build the material that we are looking at, and that concerns that we start here from isolated entities. Yeah, so we're considering materials that are made out of discrete entities, with which I can study in a well-controlled manner how light interact is going to interact with these individual entities. And then I'm trying to derive actually all emerging features from much more complicated materials from the scattering response really of that discrete entity from which these materials are made. So these structures can be, as it's shown here, so the sort of helical materials. This is an object we have been studying for quite some time. But this should really consider an arbitrary shape that made out of a complicated material, or not a complicated material, but rather a generic material like a metal or a dielectric or a semiconductor. And these are artificial photonic materials that are in the focus of interest. But as I already said, so I try to make a kind of comprehensive description, not just of these artificial photonic materials, but also of natural materials. And here I'm going to make the assumption that we consider materials made out of molecular entities, which will be described at the quantum chemical level as precise as we can get it. But afterwards, we are going to convert actually the way an individual molecule is going to interact with light into exactly the same form as you would do it also with artificial photonic materials. And this allows really to set up a kind of comprehensive framework can handle both natural and artificial materials. Of course, initially we study interaction of light with an individual object, but then we are really interested in materials. And on the one hand, we are interested here in disordered or amorphous photonic materials. that can be made out of arbitrary particles that are oriented in place with respect to each other, also in quite an arbitrary manner. But of course, we also look into periodic materials where we have identical unit cells periodically arranged in space, and where we try to describe then the optical response from those materials in terms of reflection and transmission, and to derive also properties that are of interest for those type of materials. And of course, the holy grail of our work is to look into the combination of those artificial and natural photonic materials. So where we try to combine molecules or molecular materials with supporting photonic structures in order to enhance the light-matter interaction. And it's this sort of hybrid system here that we would like to describe in a self-consistent way, in a kind of multi-scale modeling approach, quite comprehensively. Just keep in mind, so this picture should confuse you. This is, of course, not up to scale. So the molecules of interest here are typical dimensions in the order of a nanometer, even smaller. And these artificial photonic materials have typical length scales in the order of a few hundreds of nanometers. But as you will see, this T-matrix approach, as we are going to use here, is nicely suitable actually for both of these length scales, and it can bridge them. For the talk, I would like to keep you a little bit that structure here in mind, because this is not just the overview of topics that I would like to address, but this is also more or less the outline of the talk that I would like to give here. So initially, I'm going to look into description of isolated objects, study then disordered materials, and go then to periodic materials. And these sort of hybrid systems are discussed at both of these levels, suitable. Of course, so we are doing this type of research mostly from a kind of basic science perspective. Yes, so to understand actually and to explore so how light interacts with those materials. But of course, many of our activities are also driven by specific applications. I will not read them out here in detail, but you will see actually in the ongoing presentation here, so what type of applications we have in mind. And the intention here really is to develop tools so that can be applied to the exploration of those specific applications that are mentioned here in each of these individual boxes, where we consider disordered, isolated, or periodically arranged artificial or natural elements. So just to also as a kind of introductory and to give you a kind of overview of how do we think, how that sort of multi-scale modeling approach is going to work, is of course that we have to keep in mind that there are different length scales that matter here for the different entities that we are going to look at. So if we study an individual molecule, so this requires an electronic atomistic details, yeah, of those systems. So characterized here by a typical length scale in the order of an angstrom or maybe a nanometer at most. And this is clearly then the realm of chemistry, or let's say material science. And we need technology basically at the density functional theory level in order to describe properties of those molecules quite precisely. So we have a second length scale that matters for us, and that is then this mesoscopic or microstructured length scale. That we can consider either as the length scale that matters for the individual building blocks from which artificial photonic materials are made. So this is then a fraction of the wavelengths, but not much smaller than the wavelengths, but rather comparable to the wavelengths. But of course, we are also thinking about periodic arrangement of molecular materials. So from which a kind of mesoscopic material property emerge in terms of an effective material parameter. And it's mostly that aspect here, so that length scale that we're going to concentrate on most on, because the scattering language that we apply for treating these systems is very adapted to structures of that size. But of course, then there is also the sort of macroscopic device level, so that can be characterized by many hundreds of micrometers or even millimeters. And it's a final device or a really application that exists on that sort of macroscopic length scale that we would like to describe, of course, as well. And this is then really so to bridge these different length scales here in a kind of computational framework, so that allows to reach, let's say, our ability to make conclusive statements about functionalities, and possibly also for the inverse design. And it's that sort of framework, basically, that this talk is going to be about. But again, as I already said, so this will be complemented by indications on specific applications. So just as a starter, I would just like to set a framework for the language of the background, let's say, that we are going to use here for discussion. So I understand that the person to refer when you think about scattering theory might heavily depend on your country of origin. But in Germany, of course, we refer here to Gustav Mie, that had been pioneering more than 100 years ago here an analytical theory, so to describe light scattering on analytical grounds with spherical objects. And interesting enough, he had been applying that theory at that time already to colloidal solutions, nanoparticle, which in essence is nothing else than the field of plasmonics that he has been exploring. So the key assumption, and this is the key mathematical setting that we have to keep in mind in our purpose here, is that you consider a localized object in space initially, yeah, and you consider an external illumination that is given. So that is here the incident field. And what you're looking for in that sort of scattering theory is a solution for the scattered field that is in the outer region of the object of interest. And of course, we are also interested sometimes on the internal field that is excited within the structure. But for many purposes, really, when it comes to observable properties in the outer world, this internal field is of less interest. But we can concentrate our discussion here on the scattered field. But again, this is also clear. So once you know the scattered field, then you can also know basically how the internal field of the structure is going to look. And the mathematical framework of our scattering theory here is, of course, an expansion of an arbitrary field. Yeah, so that could be here this incident or the scattered field in frequency domain into a suitable basis set that is written here down in a basis set with well-defined parity. And the basis functions are those vector spherical harmonics that carry here the spatial dependency of the fields. And you have these functions here for the incident field and for the scattered field. So they are distinguished here in the superscript. And in essence, they have a different radial dependency. So to accommodate constraints impose on either the incident or the field. So for example, the incident field should be finite at the origin, and the scattered field should satisfy some outgoing wave condition. And these constraints that you impose onto these fields are encrypted here in the respective choice of the vector spherical harmonics function. But otherwise, this is a complete basis set. And these modes that we are exploring here, so they are well defined with respect to the angular momentum squared and angular momentum along a certain axis. So these are well defined quantum numbers in that setting. And we choose usually the z-axis, but this is rather a question of convenience. So to solve the scattering problem, what we need to identify actually is for a given incident field, yeah, so which we know here, this expansion coefficient, we technically need to determine these amplitude coefficients that characterize the scattered field. Yeah. I just forgot probably one thing to say. So we are mostly dealing here with linear electrodynamics, but this formalism to a certain extent can be also extended, so to capture also nonlinear effects. But they are not of importance here, but they are also a part of developments that are ongoing by us and also by many other people. Okay, and at the heart of our scattering theory, now we reach this sort of algebraic formulation of this light matter interaction by introducing this transition or T matrix, so that connects the expansion coefficients of this incident and the scattered field in a kind of basic matrix vector product. Yeah. And in a certain sense, really, so this T matrix here, this is the most comprehensive representation, so of the properties of a scatterer, because it tells you exactly how really an arbitrary incident that is characterized by these expansion coefficients here is converted into a scattered field by that sort of process of this light matter interaction. For many purposes, we are going to use just a shorthand notation by just collecting these two elements here of this vector into a single one, and just write this short as B, the scattered field, is equal to T, the T matrix times the incident. So I just would like to remind you that this T matrix has a kind of complicated structure. So first of all, it has a substructure where it tells you so how the electric multipoles of the incident field are scattered into electric poles in the scattered field, and also with the magnetic interaction here. But then, of course, you also have the electromagnetic coupling terms that are important for many applications. So then there is a substructure for each of these T matrices here. So where the interaction of light with the different angular momentum squared are captured. So this is then nothing else than the dipole, the quadrupole, and the octupole, and so on and so on. And this T matrix just tells us how an incident dipole, or here in this special case, an electric dipole, is scattered into an electric dipole field. Yeah, so this is a kind of structure of this T matrix we have to keep in mind. So there are two aspects that I would like to highlight here. So that sometimes had been a little bit a source of confusion. So that's why I would like to mention them. And I hope this is not too boring for you in a sense that this is too basic here. Yeah. But whereas this sort of T matrix very often described in terms of a spherical coordinate system, so we consider vector spherical harmonics as the base functions. So this is by no means a limitation. And you can also express the properties of the scatterers more in a Cartesian base, where you would describe them rather than in terms of a polarizability. And this conversion here of a polarizability to a T matrix or vice versa. So this is really, there's absolutely no loss of information. And this is really just a change in the coordinate system that you use to express the properties of the scatterers. So for isolated objects, the spherical coordinate system is very much preferred. But if you put them into a lattice, you will have a kind of preferred Cartesian direction in the game. And then it might be helpful also to express this actually in terms of these polarizabilities. We stress this. So if you like to work with polarizabilities, and if you would like to think rather in terms of electric dipole moments that you induce, then this is exactly the same as working with the T matrix and thinking about that you induce here a scattered field that is characterized by the electric dipole coefficients expressed here in this B1E coefficient. So this is exactly the same. Of course, this is a conversion here is written down here for this electric dipolar part, but for higher order multipole moments, that conversion exists in exactly the same way, and you can fluidly go back and forth between one or the other formulation without any change. So the other thing is that we have written down before this T matrix in a parity base. So think of it as electric and magnetic multipoles. But very often, especially when we consider interaction of light with circular polarization with the object, a helicity base is actually more suitable for this T matrix. So where we do not consider multipoles that are well defined in terms of parity, but rather multipoles that are well defined in terms of helicity. And you can think of helicity as a kind of generalization of circular polarization. Because the field of pure helicity can be expanded into a superposition of plane waves that are all either left or right-handed circular polarized if you think about a plus or minus helicity. So this is then, again, just a change in base with a kind of suitable matrix that we can use here for the conversion. And there's absolutely no change in the content of information then contained in these T matrices. So just to illustrate upfront maybe a few of these T matrices and to visualize also how they look. So we have here the T matrix of a simple sphere, which is in that sense an isotropic object. We have here in this quarter the electric part. We have here the magnetic part, and then we have the sort of cross-coupling terms. So for the sphere, of course, this is an object with a very high symmetry. You do not encounter any coupling between modes that have different quantum numbers. So that's why this is really a diagonal matrix, and only the elements on the diagonal are non-zero. Indeed, because this is then an isotropic response, so an isotropic system that doesn't have any preferred direction. So all the entries here are identical on the diagonal for the dipole part, for the quadrupole part, and the octupole part. And these are nothing else than the well-known μ coefficients that you would find here on the diagonal. So now if you unlock specific symmetries in the object, so you would unlock also entries in your T matrix that are going to be non-zero. This is here like a ring type structure where you start to see a coupling between the dipoles and the octupole terms, but you also start to have electromagnetic coupling terms. And if you break really all symmetries of the object, so like a helical structure that has even here a tapered type of wire, so this really has no symmetry whatsoever anymore. So then this T matrix really is a dense matrix where all entries are supposed or allowed to be non-zero. Before we continue, I think really just the only remaining ingredients to this talk from the technical perspective is to convince you that you can assign a T matrix by computational means to any object of interest, as long as you're here in this realm of classical electrodynamics. And you would do so if you just take your Maxwell solver of preference, take a plane wave for illumination, so that you can expand here in this vector, and then you calculate the scattered field, you expand the scattered field as well, and then you get a certain pair of incident and scattered field coefficients here. And that is something that we have to do many, many times. And out of those many combinations of illuminations and scattered field, you can reconstruct in a kind of self-consistent manner the T matrix that is able to explain data in a kind of comprehensive manner. Of course, you can also use vector spherical harmonics for the illumination, and that would allow you to probe for a single column of this T matrix, so within a single full wave simulation. But this is a technical detail. I would not like to go here into details. I would just like to convince you that you can calculate this T matrix really for any object of interest, and that is then the most comprehensive representation of its optical properties. Just to convince you at this point, so really I just summarize here a few of the properties that are important or that you might think about. So for example, it's like the extinction cross-section, or this is an ensemble average extinction cross-section, which mimics an experimental situation where you have a larger number of these helices in a solution, so they are non-interacting, and then you would like to describe the extinction of light from that sort of ensemble. So that you can calculate just from the trace over the real part of this T matrix. You can calculate also the scattering cross-section, and from both of these quantities you can calculate also absorption cross-section. But these are like obvious quantities, yeah, so that many people have been interested in. But you can also look into some more exotic properties that are useful in the context of specific applications. And one of them, for example, here is our ability to quantify duality breaking. So that is something we have to keep in mind. So an object is dual if it preserves the helicity in the interaction process. And that means that if you want to measure how non-dual an object is, you need to measure the amount of scattering interaction actually that takes place here in the sort of cross-coupling terms in these helicity T matrices. Yeah, so this is here a measure of how non-dual the object is. So you can also look into the circular dichroism of a scatterer that just measures what's the difference in absorption with left and right-handed circular polarization. So all these quantities can be directly calculated from the T matrix if you know it. And then you can plot this here as a spectrally resolved quantity according to your interest. So also electromagnetic chirality is a quantity that we have been studying for quite some time. And I'll say some more on that on the following slides. So this is electromagnetic chirality is a theme that we have been working on, yeah, so now for quite some time. And it started with the desire to be able to measure how chiral an object is. So this definition of chirality that goes back to Lord Kelvin that has been suggesting by the end of the 19th century already that an object is chiral if it cannot be superimposed onto its mirror image by any means of rotation or translation. And this is a quite strong, quite easy to appreciate definition, but it's also limited in a certain sense because it tells you that chirality is a binary property and you cannot really measure how chiral an object is. And in a slipstream of that sort of missing link here, so many geometrical definitions of chirality have been put forward, but they all suffer from a logical strange behavior, yeah, and a kind of non-consistent type of answer these measures would give you. And that's why we went back and we have been resorting and we have been defining something what is the electromagnetic chirality. So based on the interaction of an object with light of different helicity. And the appreciation of electromagnetic chirality basically starts that an achiral object should interact with light of plus and minus helicity in exactly the same way. So in order to measure how chiral an object is, we simply need to measure how different the optical response of an object is with respect to plus or minus helicity. This is the guiding idea. And quantifying this is possible then by means of the singular value decomposition of these T matrices here that encode the subspaces with plus interaction and with minus helicity interaction. Then we take these vectors and simply introduce the electromagnetic chirality as the distance between these vectors. So here in this sort of least square sense. And in order to get a normal electromagnetic chirality that is bound between 0 and 1, we can normalize this electromagnetic chirality here by what we call an interaction cross-section, which leads to an upper bounded value of the electromagnetic chirality. Just to say so, so if you have an object that is maximum electromagnetic chiral, so this is a quite peculiar object because that would not interact with light of one helicity, whereas it strongly interacts with light of the opposite helicity. And this is quite appealing. So for many applications, so like helicity filtering glasses or chiral set devices, so these type of materials are very useful. And that's why there is an open question. So can we design objects that have a very high normalized value of electromagnetic chirality? And here work that is currently still under review. So we have been using a Bayesian approach, so to optimize with techniques from the field of machine learning, so the geometrical parameters of the helix, because that helix was known to be a maximum electromagnetic chiral scatterer at very far infrared wavelengths. And we try to identify the parameters that make object maximum electromagnetic chiral also towards the visible. So this is made here out of silver. So this means that silver loses its plasmonic properties towards the visible part of the spectrum, which leads to a kind of degradation of this normalized electromagnetic chirality. But down to a wavelength of 2 micrometer or 3 micrometer, we can see very large values of the electromagnetic chirality, which made us at least quite happy to see this. So we can illustrate a little bit the optical properties of those type of scatterers here for design wavelengths of 3 micrometer. So we really see that it interacts strongly with one helicity. Here we have a peak in the scattering cross-section, whereas it basically doesn't interact at all with the helicity. So keep in mind, this is a logarithmic scale. You can also take a look into the near field. So basically, there is no interaction or no notable interaction here with one helicity, and then there is a strong interaction with light with the opposite helicity. So going further, I think I have to collect now also the representation of the discussion of the properties of the individual molecules, and to fuel them into the sort of T matrix formalism. So I admit, so this technical aspects here that would go beyond the scope of such an individual lecture. But in a nutshell, I would like to assure you start basically from at the DFT level. So to calculate the ground state electron density of an individual molecule. And this ground state electron density then contains all information from a quantum mechanical level on the properties of the molecules. And then what we are going to do is we are making a time-dependent density functional theory, whereas ground state electricity is perturbed due to an external electric or magnetic field. And it's the in this first order perturbation theory, in essence, the expansion coefficient of this first order perturbation term, so to this ground state electron density, due to an electric and or magnetic field, is the quantity that we are going to calculate here. And the molecule considers or continues to be considered here at the exact level in a DFT sense. And the properties of these molecules here are captured in this matrix B. So this has all the details like a Coulomb interaction, exchange correlation. Can also accommodate here a presence of an ambient or a host in which the molecule is embedded to. So to reflect a modification really of the electronic properties of the molecules also due to a presence of a host material. And what we can do, so we can calculate then out of this induced response, so this perturbation due to the excitation, so we can calculate the dipolar polarizability of an individual molecule. Yeah, so by basically swapping here between electric excitation and the magnetic excitation, so we can calculate the dipolar polarizability up to the bioanisotropic term. So in that sort of formalism. And then we really have here attend so the polarizability of this of this molecule. And if we have this polarizability of this molecule, so we can directly convert this again to a T matrix that represents the optical properties of the molecule. And this is then exactly the key. So to put all the formalism that we've been previously applying, so to artificial photonic materials, we can apply now in exactly the same way also to natural materials made out of those molecules. I stress this so that we just consider here the dipolar polarizability. So there's absolutely no limitations. So these field operators here can be arbitrary higher order multipolar field operators. But for practical purposes, because the molecules are so small, this is barely necessary to consider anything beyond the terms. Yeah, but this is so to achieve kind of a self-consistent description also of an individual molecule within the framework that we have. And then we can apply exactly the same formalism as we had it before. So to calculate, first of all, properties of an individual molecule. So this is here a decamphoric acid, a molecule that at one moment in our life, because of its chiral properties, but you can directly calculate here the extinction cross-section, so the scattering cross-section and also absorption cross-section from this molecule. So you can study this duality breaking, the circular dichroism, and you can also quantify how electromagnetic chiral that individual object is going to be. So once you have calculating the T matrix of that individual structure, yeah, and this is quite powerful, and this will be then the key actually on how to go also to more complicated photonic materials. So, and this is now exactly this transition. So we are maybe halfway through the presentation. And now I want to go beyond individual objects, but I would like to study the optical response of clusters or ensembles of many objects here. Yeah. And in this T matrix formalism, this is actually quite convenient. So the situation we're going to look at is that we have an arbitrary number of individual objects that are arbitrarily placed and rotated with respect to each other. And we can nevertheless describe this in a very compact notation here in such sort of matrix vector product. So the logic behind this equation gets clear in a second. Because what we see here is actually nothing else than the external illumination expanded in the local coordinates of each individual scatterer. And if we neglect this part here, the following, which is going to describe then the interaction, we are going to see that the scattered field from each object is simply the multiplication of this T matrix with this vector characterizing here the external illumination. But now the object is not isolated, but all the other objects exist as well. And that's why we need to add this nice term here, which is nothing else than the scattered field from all the other particles that we are going to convert with these conversion matrices into an incident field on any other particle. Yeah, and that information, so that is contained here in these matrices, this is quite useful. So please keep in mind here, so this diagonal here is 0, because evidently the scattered field from the object cannot be converted into an incident field on its own. So that's why there is no coupling here on the diagonal, but all the other elements are non-zero and are set zero here. So this equation nevertheless still looks a bit strange because you have the scattered field coefficients here on both sides of the equations. Nevertheless, this is quite straightforward, and you can write a kind of compact notation that suddenly looks like as if would be a kind of ordinary non-interacting process here of many scatterers, because you have this local incident field, and then you have the scattered field here of each particle. And then you can reach, or they are connected again simply by a matrix vector product. Yeah, this expression that is here, of course, this has this local T matrix, but then it also has a term that we try to understand as the renormalization of this T matrix due to the interaction with all the other particles that are going to form the ensemble here. Yeah, but again, so you can calculate this out, and then that would be just one effective T matrix. And the type of equation that we have to solve at the end is exactly the same again. And maybe just to give you an idea, so nowadays we can handle so up to 500,000, maybe a million of different particles. Of course, this is computationally challenging, but this is possible nowadays to solve that system of equation. And this is really macroscopic large materials that we can handle. There's one aspect, but maybe this is not so important here. So you can also combine the response of a larger number of particles. So you like to speak here in terms of a cluster into a single global T matrix. And with this, you can reach, let's say, higher levels of aggregation in your description, because then the details of this cluster are lost. And the object or this cluster itself is characterized just by a single T matrix. But this is maybe just for numerical convenience here. So some field of applications where we have been applying this in the past years. So this is here a metasurface, a Huygens metasurface that is made out of these high index disks. And the geometrical properties of these disks have been tuned in such a way that at normal incidence, you will excite an electric and magnetic dipole moment of equal strength. Yeah, and this sort of Huygens regime, so that allows actually to suppress any back reflection, and we have a perfect transmission. And the phase of this transmitted signal as a function of the wavelengths covers here a range of 0 to 2 pi, which makes it extremely appealing for display devices or for holographic type applications. Yeah, and we have been wondering, so what's the change, or what's the impact actually of disorder in the response of these samples? And we have been encountering something very interesting, because at the critical level of this disorder, you are going to have what we would a phase transition between a normal dispersion and an anomalous dispersion in the phase of this transmission signal. So for this periodic type metasurface, you have a normal dispersion. So there is an increasing wavelength. The phase of this transmitted signal is going to get reduced. But if you reach a critical level of disorder, you suddenly go from a normal dispersion to an anomalous dispersion. And interesting enough, so this happens at the point where actually there is no transmission in forward direction, and the structure, the metasurface itself, behaves as a perfect diffuser, which we published here in this article just recently, and which finds then, or which can find many applications, because really you have a diffuser here that is encoded into an ultra thin surface that at the end of the day is just limited by the thickness of these disks here. So one can do a bit more analysis. So one can study here like a phase diagram we have been setting up. So where we distinguish between blue and orange here, between normal and anomalous dispersion. And we can also change the spectral detuning between the electric and magnetic resonance, which gives rise to an overlapping resonance of these both resonances, or clearly split resonances. And this allows basically here really for a classification of the type of transmission property in each of these combinations of disorder here in spectral detuning, which was a kind of quite nice way. An example also for this molecular materials I also have here, and that is a system. So this is again, so this decamphoric acid. So that is a chiral molecule on its own. And we have been looking into what's the optical response of an ensemble of these individual molecules if we attach them here into such a cross-shaped type of structure. And the reason why this structure is quite nice, so this is from the molecular level, this is still really at the upper limit of what you can accommodate in your TD-DFT simulations. So you can generate a kind of reference simulation, but you can also study this optically only, meaning that you know the T matrix of the isolated molecule, and then you can arrange 4 of these objects and just derive the circular dichroism based on a consideration of this T matrix. And indeed, so this is something that works quite nicely. So there are a few details here on how exactly to calculate this T matrix, depending on whether you consider really an isolated molecule or a molecule that is embedded in a charge that, or in a static dipole that represents the other molecules. This is a small detail, but in general, we can describe this here very nicely. So in this spectra, it's worthwhile to say we have these features here that are a part of the intrinsic properties of the molecule, but we also have this feature here at 140 nanometer, that is actually not supported or not to that extent supported in the isolated object. And this is an emerging feature, so an emerging chiral feature that comes from this particular cross-type arrangement of these 4 molecules. And that response to that feature is then also very sensitive to the spatial separation of these 4 molecules forming the cross. This can be studied here. So blue curves are curves where the molecules are very close to each other. Red curves is some sort of intermediate separations, and black is some sort of larger separation. For these blue curves, when they are very close, so we see that these reference simulations and these T-matrix simulations are not in very good agreement. And this is then also, this is a clear indication for the limitation of our approach, because if the molecules are so close that charge tunneling or charge transfer processes take place among the molecules, that would be evidently something that we do not capture in our optical description. So because this is a quantum chemical effect and we cannot accommodate this. The separation of the molecules is sufficiently large, such that these chemical interaction processes are suppressed, so we can predict quite reliably actually the emerging properties that is still not contained in the individual molecule, but really just a property that emerges from that cluster, and that made us at this time quite happy that we can express this. Coming further to the last part, basically, is also the description then of the optical response of a periodic cluster. So here we really think about a periodic arrangement of identical objects and under a fixed lattice. And we want to continue actually within the same formalism, the optical response, then in terms of reflection and transmission from those objects. And the description is really, this is more or less exactly the same. Except that it's sufficient here for us to concentrate on the optical response of some central element. Yeah, so that is technically arbitrarily chosen because the lattice anyhow is infinitely extended in all 2 dimensions. And then we have this external field and this T-matrix again. And then we have here the sort of lattice summations that take place over all discrete lattice sites, where the scattering response from all objects basically is converted into an incident field of this central that we looked at. And now the cool thing is, if we know that we have identical particles and plane wave excitation, so we know that the scattering response here from all these objects, they are trivially linked to each other with a certain phase retardation, where the sort of phase retardation that emerges here is simply the consequence of a different phase at which each of these particles is excited. If we choose a plane wave here for illumination. Yeah, so this plane wave has then a phase variation across the area, and that's going to lead to a phase variation in the response. With this sort of detail, so we can reach up again a super compact type of notation to calculate these dipole moments that are induced for a given system. And from these induced dipole moments, then we can easily calculate reflection and transmission from the area. We can also stack individual arrays of these metasurfaces that can be made out of different particles, and set up a kind of transfer matrix technique also to calculate reflection and transmission from these stacks of matrices. This is a process that is very, very efficient once you know the T-matrix of an individual object. And just to demonstrate that sort of strength here, of course, we have a kind of extreme example chosen, and that is that we want to optimize so the kind of light trapping structure for a solar cell. So where we have here a kind of rudimentary type solar cell structure, and this anti-reflection coating here should consist of these disc-like structures, yeah, so that we are considered to be identical, but we still have a lot of degrees of freedom, and these degrees of freedom is here the geometrical unit cell, yeah, that this metasurface is going to mate of, and also the lattice constant, so the lattice period is also a parameter that we can flexibly adjust. And then there's a question for so which lattice parameter and which lattice type is most suitable to suppress here this reflection. And that's why we have basically integrated the reflected power weighted with the AM 1.5 spectrum here. So this is the solar spectrum from the sun. integrating this up to get like a single number that tells us how much current at the end of the day is lost in the solar cell due to reflection. And we can make extensive parameter sweeps over all these geometries. And really, once you know the T matrix of the individual object, so it costs you only 4.6 hours so to scan all these configurations here. Whereas if you have wanted to make the simulation use finite element methods, it would have taken 2.6 years on the same computational infrastructure. And this is quite an improvement. And of course, this is then attractive really for systematic design questions, also for specific applications. But one can also go further. So one can also strip down actually this sort of numerical expressions under a few assumptions, such that even analytical statements are possible about all properties of metasurfaces. And this is here demonstrated at one example. So just as a reminder, so the properties of the unit cell itself are captured here in terms of this sort of renormalized T matrix, where this is here the sum over all these lattice sites, which is something actually that can be pre-calculated and that can be stored for a particular lattice. And then you can decorate this lattice here with different objects in order to calculate different effective T matrices. And here, so we can, you can read this up in this paper that is actually already online available. But we can ask ourselves, so for example, just one example really, so what are conditions under which we can excite here resonances in these metasurfaces? And a resonance is then clearly associated to a denominator that is 0, so that it really drives this effective matrix here effectively into a divergence. And that sort of condition here can be written down rather easily. So it turns out that this resonance condition, this is nothing else than a bound state in a continuum. And we can analytically explore the existence conditions of these bound states in the continuum by making just a few assumptions on the details of our metasurface. So again, so this is not strictly necessary, the type of assumption that we do here, but that should rather illustrate a way how to strip down these sort of complex expressions into easy and handy equations that you can really use on analytical grounds. So what we restrict ourselves here is that we consider this metasurface to be made out of isotropic particles, so just spherical scatterers you can think of, characterized by an electric dipole moment, a magnetic quadrupole moment. We consider a sub-wavelength arrangement, so only a zero order propagates in space and a square lattice. And then this equation over here, that can be written down in a very compact notation into such form where we have here a modified electric dipole and a modified magnetic quadrupolar Mie coefficient that are modified at this point due to interaction with itself inside the lattice, but also due to interaction with the other multipole moment that characterizes the scatterer. Yeah, and this is like one particular lattice coupling coefficient that appears here already at this level. So these are in essence, these are renormalized Mie coefficients here. Yeah, and they can be expressed also analytically. And so all this can be written down. So there's nothing else than a few more coupling matrices appear here. And out of this equation, if we write this down, so we clearly see that this is a kind of single equation that needs to be met in order to assure the presence of a bound state in the continuum. And practically speaking, so this is applied in such a way that we are going to use a parameterization of these Mie coefficients. So this parameterization happens using so-called Mie angles that go between -π/2 and +π/2. And by sweeping through this Mie angle, we can express any possible Mie coefficient that this A1 and this B2 might attain. And if this Mie angle is chosen to be 0 degree, then we are off resonant. And if this is -π/2 or +π/2, then we are exactly off resonant. Yeah. And what we can do, for example, so we can fix in this equation this electric dipole Mie coefficient. And then there are two parameters that are left over. So in essence, the angle that parameterizes here the magnetic quadrupolar Mie coefficient and also the lattice constant that characterizes the metasurface. And these two parameters need to be identified in order to be a solution to this equation. And indeed, this can be then analytically predicted. So there's then a certain combination of period and magnetic quadrupolar me angle that tells you exactly at that point you are going to have a bound state in a continuum. This is something that we can also substantiate then by numerical simulations. So what you see here is transmission for this configuration. So it's a electric dipolar resonant object. And then you swap here the magnetic quadrupolar me angle between minus pi over 2 and plus over 2, and you change it to period. And then you see exactly in this transmission plot here, this bound state in the continuum emerging, that you can also see a little bit more in detail in this figure here. So where if you would just slightly detune the me angle that quantifies here the magnetic quadrupolar excitation, so you're going to see here the sort of super sharp resonance that can be exploited then for different purposes. So the last details or last examples, I just would like to spend a bit on the sort of multi-scale modeling also. And one of the first applications where we have been applying it was to answer the question of whether we can observe actually strong coupling in a layer of molecular material if this is coupled to a resonator. And the resonator here is rather simple, but nevertheless, these are exactly experiments that have been done in the literature. And in this case, this is here a rather thick silver metal, and this is a thin silver metal. So this is like semi-transparent metal here, or semi-transparent mirror, and one can excite then in this cavity standing wave resonances with increasing order. So these just Fabry-Perot type resonances are indicated here in this color scheme. You put this molecule in there, and you would like to study of whether the excitations in that molecule can strongly couple to these resonator modes. And the procedure here is then straightforward. So this is a molecule called this is a zinc-based phthalocyanine. So which can be experimentally arranged even in a periodic manner, thanks to a technique called surface anchored metal organic frameworks, so SOMOF in short. And this is really a periodic arrangement of these molecules, and this is like a layer process that is used for their fabrication. And then you can really fabricate like a finite thickness of that molecular material layer between the silver mirrors, in order to study then spectroscopically the properties. And we have been discussing this. So we started actually with a kind of basic absorption spectrum of a unit cell of that SOMOF structure, where we calculate here the oscillator strength, which is then nothing else than the absorption cross-section directly in TDDFT, and also from the polarizabilities that we have been assigned to the molecule. And the perfect agreement here is an indication to us that this is something that works quite nice. And then the experiment is like this, so that we study here the transmission, or this is actually absorption through this molecular layer as a function of its thickness. And we see that these individual absorption lines here just translate to a strong absorption in the bulk material. And then we can also study the absorption inside the cavity. And maybe just worthwhile to mention, so the experiment to which we have been referring here in the simulation that studied the absorption actually in the system for a film thickness of 400 nanometer, and it had been experimentally identified. So at the spectral region where there's a single absorption line here, if you couple us to the modes in the cavity, you are going to see a strong absorption line here and a strong absorption line here. The picture is probably a bit more impressive if you just would look into a line plot. But experimentally, the people really just have been seeing here these two lines, and the emergence of lines was considered as an indication of strong coupling, because that is the smoking gun for strong coupling. So nevertheless, in our multi-scale modeling approach here, so we have been quantifying, first of all, the optical properties of this molecular material in terms of an anisotropic dielectric function. So nevertheless, the anisotropy is rather small and can be neglected for the sake of this argument. And we can just quantify it in terms of refractive index. And using this refractive index, we can calculate the dispersion of the modes that are supported in this Fabry-Perot cavity. And then you see actually here already that these modes are quite distorted because the refractive index here at very high energies, or at energies higher than the resonance, is pretty small. And at wavelengths longer than the resonance, that at shorter energies, the refractive index is pretty high. And that leads to quite a distortion here of these individual modes. And then we can plot these curves above each other. And then indeed that we see that this absorption curve that we spectroscopically compute can be very nicely explained actually based on these modes. And here we see actually that at least what had been previously observed experimentally would not qualify as to call it a strong coupling, because these two lines that have been seen, which are then left and right to the absorption line of the individual molecule, is not the splitting of the same mode, but they have been corresponding rather to two different modes of the same cavity that exist here for the same thickness of the film, just at slightly different frequencies. And these are two modes really in the same spectral region here, because the material with which you fill the cavity shows such strong dispersion that didn't make this so obvious at first glance. Yeah, and which was only possible really to study here, because this is a kind of accurate multi-scale modeling that allows us to represent optical properties of these molecular materials in more macroscopic optical simulations. I think I have one more example, but I might skip this also in the interest of time. So this is like a perfect absorber, so that we studied made out of individual gold clusters, where we started here with a quantum chemical description of the individual gold cluster, studied then the response of a larger number of these gold clusters that form an ensemble. We have been assigned then effective properties to this material, and with these effective properties we can design, or we can optimize here a perfect absorber that consists of a metal nanoparticle layer, a dielectric spacer, and a metallic back contact here. Yeah, but this would be just another example for the same type of formalism that I've outlined before. So this brings me then to the summary. I hope I could convince you that this multipolar approach here based on this T matrix, so this is very versatile and provides physical insights into the effects that you can encounter in photonic materials. Yeah, and it also constitutes a very good design tool. The limitation that we have here is that it revolves, let's say, mostly around materials made from discrete entities. Yeah, so because it's the T matrix of discrete object that you have to determine very precisely. But once you know this T matrix of this individual object, you can easily go to much larger architectures and to describe here very nicely the optical response. The materials that we can assess here, so these are natural molecular materials, so disordered amorphous materials, gratings, metasurfaces, also photonic crystals and metamaterials. So all these things can be done. So I stress this. So here we have been restricting our attention mostly to the local bioanisotropic response. But indeed, there are also other extensions and effects that we currently explore. So this concerns like a nonlinear description, and even effects like Raman can be possibly described, and also other things. This is like a numerical tool, but you can also strip this down to analytical expressions in order to have really a very convenient language in order to discuss properties really on a sound physical ground. Yeah, I think that's it. So I thank you very much for your attention, and I'm very open for any question that might come up.
Thank you so much, Carsten, for this wonderful talk. So, like you said, anyone who asks questions is really welcome.